And so some time ago, Umesh asked me if I could come to this boot camp and talk about the PCP theorem. I said that maybe with 4 or 5 hours I would give an introduction, but I wouldn't come to Berkeley in the morning. And then Umesh said, oh, perfect, no problem. You start at 9:30 and you have an hour and a half. So I'll see what I can do here. So first I want to describe two equivalent statements of the PCP theorem and their equivalence. This is a very simple equivalence, but very useful because some arguments are much more natural from one point of view and some other arguments are much more natural from the other. So a lot of complications can be saved by having in mind this ability to switch from one point of view to the other. And I'll also discuss the parallel repetition theorem. Which gives an equivalence of the PCP theorem to a kind of highly non-trivially equivalent other formulation. And then I want to say something about the two known proofs of this theorem. The original proof from 1992 and Iridino's proof from about 10 years ago. But in the interest of time, instead of trying to really describe all the details of those arguments, what I will do is to describe two constructions of error-correcting codes. They contain all the conceptual ideas that appear in these proofs. And then, as time allows, I'll describe how those proofs actually work and what are the technical difficulties that come up in implementing those ideas that are very simple to apply to construct codes in order to actually prove the PCP theorem. So the original proof sort of corresponds to algebraic construction of error-correcting codes using also concatenation. And the inverse construction corresponds to a construction of error-correcting codes using expanders. That doesn't really make a lot of sense as a construction of codes, while those are actually fairly good codes. But it's just a very good model of what goes on in this proof. Okay, so let me begin from the statement. And feel free to ask any questions. So in the first statement, so we start from some NP-complete problem, like tree-coloring or tree-sat, let's say tree-sat. And the statement says that there is a reduction, polynomial time computable. So this is a polynomial time algorithm. That given a formula, given input to tree-sat, given a 3CNF formula phi, constructs an instance of a problem that I will call 3CSP for Boolean constraint satisfaction problem with 3 variables per constraint. Let me say here how it looks like. An input to a 3 constraint satisfaction problem is something where there are Boolean variables. It's just a slightly more general version of tree-sat. There are Boolean variables. And then there is a collection of Boolean constraints each with at most 3 variables. So for example, an input of 3 CSP could be something that says the constraint x1 equal x2 and x4, the constraint x2 or not x3, and then the constraint x1 equal x2 XOR x3. So, and the goal would be generally to satisfy as many of those constraints as possible, ideally all of them. 3SAT would be the special case where every constraint is the OR between 3 variables, possibly with complementation. So the claim of this theorem is that there is a reduction, takes some input of an NP-complete problem, constructs a collection of Boolean constraints of this form, with the property that if the original input was satisfiable, then the constructed 3 CSP problem is satisfiable. And if the formula is not satisfiable, then every assignment to the variables of the 3 CSP problem contradicts some constant fraction of the constraints. And here, epsilon is some absolute constant. In fact, for this statement, epsilon could be 24% with the using more recent proofs. So in this form, this is a statement about complexity of approximation. It says if you are looking at Boolean constraint satisfaction problems, even if they are fairly simple constraints with just 3 variables per constraint, it's NP hard to get approximation beyond some constant factor. Now the term PCP in the term PCP theorem, PCP stands for probabilistically checkable proofs. Well, here this is a statement about hardness of approximation, and so checking of proofs, it's the second equivalent point of view about this theorem. So let me describe how from this one gets to think in terms of proof checking. Okay. So suppose that we know that something like this is true, such a reduction exists, and suppose we're given a Boolean formula phi. So a witness or a proof that the formula is satisfiable would just be an assignment to the Boolean variables that make the formula true. But we can think of, given this reduction, about a more complex, but also more interesting witness or proof that the formula is satisfiable, which could be the following. You could compute the 3 CSP let's call this reduction R. So compute R of phi, and then define a witness that phi is satisfiable as a satisfying assignment for this constraint satisfaction problem. Now, suppose that someone gives us a Boolean assignment with the claim that it satisfies the constraint satisfaction problem coming from this theorem, and hence witnesses that the Boolean formula is satisfiable. Well, instead of just looking at all of it, we can construct the constraint satisfaction problem that comes from the reduction. Pick at random one of the constraints, and then read the 3 variables appearing in that constraint in this assignment, and then see if just that particular constraint is satisfied by this assignment. Okay. So then what's going to happen? If this was actually a satisfying assignment, with probability 1, it will verify that constraint. But if the Boolean formula was not satisfiable, then no matter what's written here, there will be a constant fraction of those constraints that are not satisfied by this assignment. So even just picking one at random, there is some epsilon probability, or 24% probability using the best known proof, that we will see an inconsistency. And in fact, if we pick at random a large constant number of constraints, and like 100 over epsilon of them, and we look at whether they are all satisfied by this assignment, if this is satisfying, we will see that with probability 1. But if the Boolean formula is not satisfiable, there will be a kind of astronomically small probability that no matter what's written here will satisfy this verification. But you must also think of it in the following way. Like, suppose that, like, to make it even more a statement about proofs. So imagine that you are interested in proofs of some particular mathematical statement, like the Riemann hypothesis. And you're interested in whether there exists proofs in some formal language, like maybe the proof verification system COC, up to a certain length, maybe a gigabyte. Then you can certainly write a large, but not kind of tremendously large, 3CNF that will be satisfied if and only if there is a proof of the Riemann hypothesis of length at most 1 gigabyte in COC. So you could compute this reduction. This will give some particular collection of Boolean constraints over triples of variables. So then what's going to happen? Someone says, okay, I found a proof for the Riemann hypothesis. I have encoded it as an assignment for this formula. I've also re-encoded it as an assignment for this collection of constraints. Now we pick at random 100 of those constraints, and we read the 300 bits in this proof. Well, if it was valid, the whole thing will check. But the thing is, if this check is verified with probability even kind of negligibly large, that means that this formula had to be satisfiable, which means that somehow whatever is written here is in fact proof of the Riemann hypothesis. Or at least if what we observe had only a probability 1 in 2 to the 100 of occurring if the Riemann hypothesis had been false. So from a frequentist, not Bayesian point of view, you can have very high confidence that the proof is valid. Now, now there are some features of this verification. So what you're saying is that there is some verification procedure for sort of non-traditionally encoded assignments for 3SAT, such that whenever a formula is satisfiable, the verification procedure accepts with probability 1. When it's not satisfiable, no matter what is written, even if it doesn't satisfy the definition of the encoding, it rejects with some constant probability. It only looks at a constant number of bits, And the amount of randomness needed to generate the locations that are being read is only logarithmic in the size of the formula and in the length of this proof. Because all the randomness that we used was to pick at random one of those constraints. So let me write down a definition. We'll say that a decision problem, like some computation problem with a yes or no answer, like 3SAT, belongs to what we'll call PCP 1 as order of log n q. If there is a verification algorithm V runs in polynomial time, uses order of log n bits of randomness, so this is this part of the definition. Given an input x to the problem and a proof y, the algorithm will select q locations in y, will read the proof just in these locations, and then accept or reject. And here this Q is this Q. In this example was 3. And then the properties are that if we have an input for which the correct answer is yes, there will also be a proof that V accepts with probability 1. And if an input is not in a language, then no matter what proof is being presented, V accepts with probability at most at most S. Okay, and this is this parameter. And this formulation of the PCP theorem is that 3SAT, but in fact any problem in NP, belongs to such a class. There exists an epsilon. All right, now so I just want to verify that not only this statement about hardness of approximation implies this statement about checking proofs by only looking at a constant number of bits, but in fact that the two statements are equivalent.
Q is 3.
The definition is sort of valid for every parameter here. We could state the theory, then we'll see that it's equivalent under different choices of the number of queries. for now, we'll state the theorem where the special case in which Q is equal to 3. This theorem is stronger the smaller is the number of queries, because the verifier can always make more queries and ignore the answer. It's false when the number of queries is 2, and so 3 is the minimum for which it works.
And increasing the number of queries just makes epsilon larger.
It is possible to increase the number of queries and make this probably 1 minus epsilon smaller or epsilon larger by simply repeating the verification procedure several times. So we'll talk about those equivalences later, but if you repeat this k times, the number of queries will be 3 times k. This probably will be 1 minus epsilon to the k. Okay, so to state those equivalences in a way a bit more compact, let me give this just one more definition. I'll call the gap constraint satisfaction problem 1s to be the problem where we're given in input a constraint satisfaction problem with 3 variables per constraint. And we want to distinguish the case where this is satisfiable from the case where every assignment contradicts, every assignment satisfies at most a fraction s of constraints. So this statement of the PCP theorem, the first statement, is saying that 3SAT reduces in polynomial time to a problem of this form. And the second statement says that 3SAT belongs to this probabilistically checkable proof class. And so we've argued that this implies this, that if you have this kind of reduction, you can use it to give a definition of a proof checker that verifies the validity of a 3SAT formula by checking at random one constraint in this reduction. But the other reduction, I mean, it's also possible to get a reduction in the opposite direction, so to kind of clarify that those 2 points of view are completely equivalent. So suppose we have a machinery of this form for 3SAT, or actually for any problem of our choice. So we give an input to our problem. We are also given some proof. We pick at random 3 locations in this proof. We read them and then decide whether to accept or reject. And we make this selection using only a logarithmic amount of randomness. Then how do we get a reduction of this form? We could, so we can do the following. So suppose we have statement number 2. We're given an instance of 3 sats. So we will simulate what the verifier is doing for all choices of the randomness. So we'll think of the proof as being kind of parametric. Say the proof will contain some collection of bits. Let's call them y1 up to ym, which we don't know what they are. And then we see what the verifier would do over the proof for all choices of randomness. Okay. So you can say, well, suppose the randomness is all zeros, then we maybe will select entries y2, y5, and y10. And then we'll accept or reject depending on what are the 8 values of those 3 entries that it reads. And we have the code for V, so we can also figure out for each of the 8 possible outcomes of those queries what it accepts or rejects. So maybe we verify that this accepts maybe if and only if y2 is equal to y5 and y10. So then we will write the constraint y2 equals y5 and y10. Then we move on to the next possible choice of the random string. So maybe this time V with this choice of randomness selects y1, y10, and y11. And we can again simulate what it does for each of the possible outcomes. And maybe it only accepts when y10 is equal to 1. So we'll write y10 equal to 1. So we can do that for each choice of randomness because there are only polynomially many. And we construct, in this way, a polynomial size constraint satisfaction problem. And what are the properties of this constraint satisfaction problem? Well, every assignment to those Boolean variables corresponds to a possible proof in a proof system. And the number of constraints that such an assignment satisfies is precisely the number of random strings that would make the verifier accept that particular proof. So for every assignment, the fraction of constraints that it satisfies is the same as the probability that the verifier would have accepted a proof identical to that assignment. Now, if the formula is satisfiable, there is a proof that is accepted with probability 1, which means that this collection of constraints is satisfiable. And if the formula is not satisfiable, then every proof is accepted at most with probability S, which means that for every Boolean assignment to those constraints, at most an S fraction of constraints can be satisfied at the same time. So that gives a reduction of 3 sat to this kind of constraint satisfaction problem. And notice that it's with exactly the same parameters. The probability of accepting an incorrect proof becomes this fraction of constraints, and the number of queries becomes the size of the constraints. And in fact, this is true also if we look at probabilistically checkable proofs where some Q number of queries are made, and we look at constraint satisfaction problems that, in general, instead of having 3 variables per constraint, have Q variables per constraint for some Q. Right. Now, having given the definitions of those problems, so to show a couple of trivial equivalent and then one highly non-trivial equivalent formulation. Is there any question about any of this so far? So one thing, as we mentioned before, it's always possible to decrease this probability of error by increasing the number of queries. And so if you have whatever you can do just repeat the verification protocol k times independently, the number of queries will increase by a factor of k, but the probability of accepting will be, so the end of, you have to accept k times independently. Each time this happens with probability at most 1 minus epsilon, so this probability can be made to go to 0. Also, this probability here is called the soundness of the system. And the reason is that in this view where we are checking the validity of a proof, the first condition is saying that if a statement of the form x is in L is true, then there is a valid proof of that. So that's a completeness statement, true statements of proofs. And here this is saying that if a statement of the form x is in L is false, then there is no perfectly valid proof. So it's a soundness statement because it says there are no perfectly valid proofs of things that are false. And so by extension, this probability is also called the soundness probability, or just the soundness of the system. So the soundness can be made to go to 0 exponentially in the number of queries. And this also means that when you're looking at constraint satisfaction problems, when you look at constraint satisfaction problems with more variables, the hardness of approximation increases. And in general, when you're looking at constraint satisfaction problems that have some k variables per constraint, the best approximation you can get is exponentially small approximation factor in k. Sort of conversely, if you have a PCP theorem with some large number of queries, you can always bring them down to 3, maybe increasing the soundness. So if you have something like so up to the exact value of the soundness, if you prove the theorem maybe with 25 queries, it's also true for 3. And this is an implication that is easier to see in the optimization version of the problem. So let me briefly describe this. So suppose I have this approximation problem to distinguish between satisfiable and 1 minus epsilon satisfiable instances of Boolean constraint satisfaction problems with q variables per constraint. Well, this is a problem that I can reduce to the special case where every constraint is the OR of q variables. And I can do this very simply if I have some constraint involving lots of variables. I can always rewrite it as a CNF. If it involves Q variables, I can always rewrite it as a Q CNF. And this will be equivalent. But then I can just think of this collection of CNFs as just being a collection of terms. And then if this was satisfiable, this was satisfiable, and this is satisfiable. But if every assignment contradicts some epsilon fraction of those constraints, it will contradict an epsilon fraction of those CNFs. So that means for an epsilon fraction of those CNFs, at least one term is false. When you write a function of k of q variables as a CNF, you don't need more than 2 to the q terms. So here, there's at least an epsilon fraction of those CNFs in which at least a 1 over 2 to the q fraction of terms is false. So that's why the fraction that is false goes down by 2 to the q. And then there is just the standard reduction of k sat to 3 sat, where you lose an extra q minus 2. And so this reduction is equivalent to this containment. So if you have the PCP theorem with any constant, the constant can be made, with some loss, can be made to 3. And also, you can say that the verifier looks at those 3 bits and then just computes the OR of them. Doesn't do any other computation. Now, so in terms of how simple can be the procedure that the verifier employs, so here we have something very simple. There are, it just reads 3 entries. Every entry is a bit. And if it were reading 2 entries, the theorem would be false. But a sort of also minimal verification that the verifier could do would be if the proof is written down using a ternary alphabet, and the verifier only looks at 2 entries. So instead of looking at 3 bits, maybe it looks at 2 elements from a ternary alphabet. Or in terms of constraint satisfaction, it's a problem where we have variables that take values over a triple of possibilities, and every constraint is only over 2 variables. So to see this equivalence, suppose I have an instance of gap 3 sat. So this is a collection of constraints where each one is just the OR of 3 variables. So we'll construct a new instance that has actually all the Boolean variables that I had before. But also, if there are m clauses, there are going to be m new variables that will take values in 1, 2, 3. And the intuition for this new problem is that the axis will be the Boolean assignment that satisfies the formula. And those extra variables, for every clause, will say which is, say, the first variable that is true and satisfies the clause. Like maybe in this formula, setting x1 to false and x2 to false and x3 to true and x5 to true and x7 to true would satisfy those two clauses and maybe also all the others in between. And in the translation here, the x's would take the same value. Maybe true is 1, false is 2, and 3 is never used. And then, y1 would be 3, because the first clause is satisfied by the third variable. Ym would be 2, because it's the second variable that satisfies the clause, and so on. So in this new problem, the actually, this is a place where it's better to think in terms of verification than optimization. So here I want to define a proof system that makes two queries and the outcome are ternary. So here in this proof system, I have a part which is those x's, and a part that is those y's. And then the verifier will pick at random a clause, will read the corresponding pick at random a clause, and then will read the corresponding yi. Then it will pick at random a variable in the clause, and it will read it here. Now, if this was maybe the first variable in the clause, and what you read here says the second variable satisfies the clause, in those cases you always accept. But if you happen to pick maybe the first variable here, and here it says the first variable satisfies the clause, you accept only if that's actually true, only if this variable does satisfy the clause. Okay. So now we're only reading two entries in this proof, and they're only ternary. And I want to argue that clearly, if this formula is satisfiable, this process accepts with probability 1. But I also want to argue that if this formula was 1 minus epsilon satisfiable, this process has a probability at least epsilon over 3 of detecting an error. And so what's the reason? Let's look at the number of clauses that are satisfied by this assignment. It cannot be more than a 1 minus epsilon fraction of the clauses. So when the verifier picks at random a clause here, with probability at least epsilon, it's one of the clauses not satisfied by this assignment. Now, so which means it's one clause in which all the three variables in the clause are false. So the value here will point to one variable that does not satisfy the clause. Now, 2 out of 3 of the times, we're going to pick one variable that was not the one pointed at here, and so we accept. But 1/3 of the time, we're going to pick that one, and we will see the inconsistency. So with probability epsilon over 3, we see the inconsistency. Now, this type of proof system has the following properties. It makes only 2 queries, and the proof itself is sort of split into 2 parts, and the queries are made one on one side and one on the other. So this type of so I'll write what we just did. We sort of show that if some language reduces to gap 3 sat 1 minus epsilon, or equivalently 1. Then this language belongs to what we will call 2-prover 1-round proof system with parameters 1 minus epsilon over 3, logarithmic randomness, and alpha beta size 3. So here, 2-prover 1-round stands from the fact that when the verifier reads those 2 pieces of the proof, a conceptually equivalent view is that the verifier is actually interacting with 2 agents that don't communicate with each other and that are trying to convince the verifier that the formula is satisfiable. And the verifier interacts with those 2 provers in only 1 round of communication. It makes the query, gets the answer, and then gets to make a decision. Okay. And so here we're saying if the formula is satisfiable, accepts with probability 1. If it's unsatisfiable, accepts at most with this probability. And this is the randomness. And this is the range of possible answers that you can get. It's the alphabet in which those proofs are written. Right, so we also get this here. All right, so finally, the highly non-trivial kind of equivalent formulation of the PCP theorem is that in systems of this form, which are very useful for a lot of hardness or approximation applications, sort of an intermediate tool, it would be good to have systems where this error probability can be made to go to 0, maybe allowing the range of the possible answers to grow. Similarly to what we did here, that we allowed the number of possible questions to increase and letting the error go to 0. So here also we could do a sequential repetition that says, well, the verifier will pick independently k choices of what to do, and then we'll make will read k entries in this proof and k entries in this proof. But then it's no more a system where you're only looking at 2 locations. So what has been studied instead is what is called parallel repetition. This is as opposed to sequential repetition where you execute the protocol and then you execute again and you execute again. So in parallel repetition, in the prover's view, the verifier picks at random first a pair of queries that it would make according to some choice of randomness, then it picks fresh randomness and picks another set of queries and so on. Maybe it picks k of them. And then it makes all the first queries to the first prover, all the second queries to the second prover. So in this example, you would say, okay, I have my 3-set formula. I'm going to pick at random k clauses. And then here I want to see in each of those k clauses, what are the variables that satisfy it. And then here, in each of those k clauses, what's the value of a randomly chosen variable? So here the proof would consist of each entry of the proof would be k tuples of Boolean values. Here would be k tuples of triples of values. Here you get k answers. So here the intuition is that since those are independently chosen executions of the protocol, although it's possible for the answers to correlate to each other, those correlations shouldn't help. It turns out that there are interesting examples where it is possible to exploit correlations, and even if you start from a system where the maximal acceptance probability is 1 minus epsilon, here you can get something where you can do much better than 1 minus epsilon to the k. But it's still true that the probability of acceptance, even for the best proofs or the best prover strategies, goes down exponentially in k. So this shows that so in particular, if you do this k repetition, so you'll need t times more randomness. Sorry. If you do k repetition, you need k times more randomness. The number of possible answers will increase exponentially. And the theorem is that this becomes something like, I'll blow it up. This becomes something like 1 minus the cube root of epsilon to the power of some constant times k. So it's still possible to make the error go down exponentially, but in a highly non-trivial way. So it can be the error still quite a bit more than 1 minus epsilon to the k. So those are sort of various formulations. The error can be bounded away from 1 with just 3 queries. It can be made exponentially small with a linear number of queries. 3 queries always suffice. 2 queries also suffice if you allow at least 3 possible answers. And 2 queries suffice with an exponentially small error if you allow bigger answers. Now let me give some intuition for how those proofs work. And as I said, instead of trying to actually describe the proofs, I will describe 2 constructions of error-correcting codes that follow the same conceptual steps as those proofs. But I want to start from the construction and mimics what's going on in the Nernst proof, so that I think it's the more interesting one. And if we run out of time, maybe we will not see this one. So the goal will be the following. Will be to construct some mapping that takes some string of bits that we want to encode, maps it injectively into a bigger string, and we want this encoding to be at most of polynomial length. And we want it to be injective in a very strong way, that for 2 different inputs, the encodings must differ in a constant fraction of locations. So the idea is that then they could go through some channel that corrupts a constant fraction of bits, and still, at least information theoretically, we have not lost any information about the original message. In fact, normally we would want this to be linear, but the constructions that correspond to those proofs will be just polynomial. So we'll define the following transformation. That given whatever we have gotten so far, so this will be an iterative construction that keeps improving. Given whatever we got, we will define a better construction where the new construction is only a constant times longer than the previous one, and the minimum distance is twice as good. Minimum distance, I mean the guarantee that for any two different inputs, the outputs differ in at least this many bits. So I will give some transformation that takes some encoding and gets a better encoding. Better in a sense that if you look at what's the fraction of bits that differ for any two different inputs, it's twice as much. So then we will start from the identity encoding. And then apply the transformation log n times. Yeah, then it does what we want. Because initially the identity encoding, this parameter delta, in the identity encoding, any two different inputs, their output differ in at least one bit. So this parameter delta is 1 over n. Every time we do this improvement, this parameter delta doubles. So it takes at most log n times to become a constant. Now, each time the length of the encoding increases by a constant, but if we multiply n by a constant log n times, it's still something polynomial in n. All right, so I need to show the existence of this transformation. We will do this transformation in 2 steps. One step will actually quadruple the minimum distance, but the encoding will not be binary anymore. It will be over strings of some non-Boolean alphabet. And then we will half the minimum distance, but get back to a Boolean encoding. So altogether, we go from Boolean encoding to Boolean encoding, and the minimum distance doubles. And the length of the encoding only grows by a constant factor. So first, let me show how you could do that if you would allow the length of the encoding to increase polynomially. That's really not good, because if the length of the encoding increases polynomially for a logarithmic number of steps, it becomes exponential. But just to see the idea. So suppose I have the encoding of the previous step.
And then you get
Sorry?
2 to the polylog. Even if it increases polynomially log n times, don't you get 2 to the polylog?
No. So if you go from n to n squared, and then you do it again, it becomes...
Oh, I see, okay.
So it's so if you do it k times, it will be n to the 2 to the k.
Right. But even if you, so I think what Umesh says, so nothing which is non-constant is good for us. Even log, even if you multiply it with log, it's not going to be good for us.
Yes, you will not get a polynomial encoding with anything other than constant, although you could get a sub-exponential encoding with anything that is slightly superlinear.
It's like log to the log is still
Super polynomial, yes. No, but this will just be for illustration what it goes on polynomially. So I could do the following: just define C prime to be of length m to the fifth. And the idea is that if I want to compute C prime of x, first I compute C of x. So it will be this string of m bits. And then C prime, not to scale, will have like one entry for each choice of 5 entries in C of x. So that's why they're going to be m to the fifth entries. And the content of this entry will be the 5 bits that are in C of x in these entries. All right, now I want to, so what is the minimum distance of this new code? If I look at C of x and C of y, they differ in some delta fraction of coordinates. When I look at C of x and C of y, what's the fraction of coordinates that will differ in? Well, it's easier to argue about the fraction of coordinates in which they're going to be the same. So for just look at the random coordinate in this code. For the two code words to be the same, what it means is that I picked 5 random coordinates here, and they all landed in this area of density 1 minus delta. So that means that they can only agree in 1 minus delta to the 5 fraction of coordinates, so they differ in this much. So this is about 5 delta, and let's say it's bigger than 4 delta if delta is sufficiently small. So I can quadruple the minimum distance, and by using a code that is not binary anymore. But then I can also get a binary code which will be of length well, there are better ways of doing it, but let's say 2 to the 5 times n to the 5. Just by re-encoding each of those non-Boolean entries with a Boolean error-correcting code. So now this, instead of being an entry, becomes its own little encoding. Using the Adamar code, I can make it be of length 2 to the 5. All right. Now, every one entry in which those two code words were differing now becomes a whole string of bits in which those two code words will differ in half of the places. So this means that the fraction of coordinates where now these Boolean strings differ from each other is going to be half of what it was here. But this was already 4 times what it was here, so I still doubled the minimum distance.
That's actually the exponent. It's m to the 5 times 2 to the 5.
2 to the 5 times m to the 5. Huh?
About it goes from 0, 1 to the n to 0, 1.
Oh, yes. Thanks. So this is a non-Boolean encoding. of m to the 5 elements of this alphabet. Then with the re-encoding, it becomes Boolean, and the length increases a little bit. So this would work, but so the composition would destroy the code. But let's think of sort of why we define the new code in this way. So in this new code, every entry of the new code was indexed by a tuple. And what we wanted from these tuples was the property that they're going to hit a set of density delta with probability 4 times delta. Now, this is true if the tuples are chosen completely randomly. But there are also many, which means then we need to enumerate all tuples to define the code. But this is also true for pseudo-randomly chosen tuples of coordinate. So then when we enumerate pseudo-randomly chosen tuples, the code doesn't get as long as here. So one particular way of choosing tuples pseudo-randomly in a way that makes this construction work is to think about an expanded graph with m nodes, so as many as the coordinates of our code, and constant degree. So in this graph, there is a node for every coordinate. So when, in particular, we think about the encoding of some x and encoding of some y, there will be some delta fraction of nodes that correspond to the coordinate in which they differ, and one more delta in which they don't differ. Now, something that is true about expanded graphs is that if one constructs a random walk in the graph, so starts from a random vertex, then moves to a random neighbor. This is a probabilistic process, then moves to another random neighbor, and so on. And say we do that for 10 steps. Well, then the sequence of 10 nodes generated in this way is something that could be done in only m times some constant to the 10 different ways. Because random walk is defined by the first vertex, and then at each step you only have a constant number of choices to make. So there are only constant times m walks of this way. Nonetheless, a random 10 tuple chosen in this way has many of the statistical properties of just picking 10 vertices uniformly at random. In particular, this will depend on the degree and the expansion, but for a set of vertices of density delta, this process has probability, say, more than 4 times delta of hitting that set. But for sufficiently good expanders, even 5 steps would be enough. So given this fact, instead of constructing C prime to have one coordinate for every 5 tuple of the original code, I'm going to construct C prime to have one coordinate for every, let's say, 10-step random walk in this graph. Okay. So each coordinate will correspond to 10 vertices, but not all choices of 10 vertices, only 10 vertices that could be in a random walk. And then the content of this entry will be whatever the code was containing in those 10 coordinates. Okay. So now, what is the length of this encoding? I have so this is what each entry is like, and then a number of entries is m times the degree of the graph, which is a constant, to the power of 10. Or maybe 9, if that's the first vertex. If there will be a much more complicated expression here, but if the expander is sufficiently good and delta is sufficiently small, I can make it so that a tensor-type random walk hits this set with pretty 4 delta, so that any two encodings will differ in a 4 delta fraction of places. Then I will do the Boolean re-encoding, maybe it will be a little bit bigger here. And so this will be my final encoding length. Order of m, because there will be m times some constant many coordinates, each one having 2 to the 10 bits. And now I do have this property that in the new code has linear length and twice as much distance. And in so in the Nurse proofs, she proves the PCP theorem in this form. And so what corresponds in this construction is that the length of the encoding sort of corresponds to how big is the constraint satisfaction problem that she constructs. And the minimum distance sort of corresponds to what is the soundness in the construction. So she starts by saying that sort of 3-SAT itself is a gap problem where this is just the number of clauses. Because it's a problem of deciding if it's all satisfiable or if at least one clause is contradicted by every assignment. And then she gives a way of saying, well, start from some input x of there are various ways to set up this induction, but let's set up this way. And then you apply this reduction a logarithmic number of times, and you get the PCP theorem. Here, this delta needs to be sufficiently small. Now, this reduction works in 2 steps. There is also, it's a combination of 2 reductions. So one reduction will increase the soundness error by, say, a factor of 4. But then the problem will not be Boolean anymore. And then she has another step where the problem gets back to being Boolean, but this error gets worse by a factor of 2. However, what you gain in the first step in error is more than what you lose in the second step, and so you have this improvement. And each of the steps increases the size of the input only by a constant factor. So the step where the problem becomes problem with a better soundness error and a non-Boolean character is sort of similar. It involves random walks in expanders. So one constructs the new problem in a somewhat similar way. And the step where you turn the non-Boolean problem into a Boolean problem has sort of a nature of encoding non-Boolean information with an algebraic code. Okay, so I'll describe the construction of codes that are more in the spirit of the original PCP theorem, and there. There the connection is even looser, but just give at least a couple of ideas of what the argument looks like. So here we're going to do completely algebraic encodings. So we're going to start from the following observation, that if f and g are polynomials, univariate polynomials of degree d over some field, then they agree on at most p inputs, different polynomials. So this gives rise to a good non-Boolean error-correcting code, the Reed-Solomon code, where if you have some n bits of information that you want to encode, you can map them to a something like this. In the following way, you fix a field of size n. Maybe n is not prime, but of size between n and 2n. Then you observe that there are 2 to the n polynomials of degree n over log n. Because each polynomial is specified by these many field elements. Every field element encodes log n bits, so every such polynomial encodes n bits. So fix some, those are all easy to compute, some bijection to n bit strings. So then n bit string x will be mapped to a string of this form. But what I mean is that f sub x is, according to this bijection, some polynomial that corresponds to the n-bit string x that we want to encode. And the encoding is the evaluation of this polynomial at 2n divided by log n locations. Now this is a good code, because if I'm looking at a different input, this will be a different polynomial evaluated at the same collection of inputs. But if those are two different polynomials, they can agree on at most as many locations as the degree, which is n over log n. So they can only agree on half of the inputs. And this can be instantiated differently, but always gives rise to excellent codes. But now those codes are not Boolean. In fact, each entry has not just a constant, but even n possible values. So this will be some encoding where every entry is something that contains log n bits of information. But then again, if we re-encode every entry using a Boolean code, although it's wasteful, we could use again the Hadamard code. So this would become n bits, and the whole thing would be of length n squared over log n. Well, then for every two code words, before the re-encoding, they differ in half of the positions. After the re-encoding, in half of the positions, those have become bit strings that differ in half of the bits. So overall, the two Boolean code words differ in a quarter of the positions. So if you wanted better efficiency, also shorter length, you could do this in two steps. So first, encode each position with an exponentially smaller code of this form. So now each position would have only log n possibilities. And then encode that with the Hadamard code, and then it only blows up polylogarithmically. Now the in the original proof of the PCP theorem sort of involved two ways of constructing probabilistically checkable proofs. One had Boolean proofs, but required the proof to be exponentially bigger than the three-step formula that you wanted to prove satisfiability of. And then there was another system that had polynomial length proofs that you only need to look at into a constant number of places, but each place contained polynomially n bits of information. So then what I did was to combine those two proof systems, much in the way that you would concatenate error-correcting codes, so that you have one Boolean proof system that tells you that a location that the original proof system would look at would make that verifier accept. And now this is a statement about something that is only of logarithmic length, even if it's encoded exponentially, it's polynomial. So a bit like here, you use a code that has an exponential blow-up, but you don't apply to the whole information, you only apply to something that has n possibilities or that contains log n bits of information. Okay, so I guess those two toy models are as much as I can tell about the two proofs of the PCP theorem, and maybe it's a good place to stop. Yeah, thank you.
Questions?
Finished 1 minute early too.
Is it good or bad?
I'm sorry.
Is it good or bad?
It's excellent. And
I have a question about sort of the history of the Genur proof came quite a bit later. Is that true?
yeah, about 12 years later.
So, do you have a reason for why that would be?
She was quite young.
Well, I guess like people have been thinking about hardness approximation for a long time before the PCP theorem. It seemed very hard to get reductions that would sort of go from Turing machines or NP completeness and get you hardness of approximation. It always seemed you can only gain or lose a little bit in approximation, and that you needed something completely different to do this jump. So then when this idea of proof systems came up, then there was this revelation, this is precisely what's needed for hardness of approximation. And the sense was that without this, there would be no other way of doing this jump. And the thing is that you could try to sort of, as Reed did, to do things in stages, but unless, even if the length of in your reduction blows up by log n, you end up with a super polynomial reduction. So it just didn't seem that any kind of gradual approach would work. And I guess Reed was not bound by conventional wisdom. And
I guess Spearman Zipser tried to do something like that early on, right? But they were
actually,
missing
that's
something.
true. They had the expanders and they had this notion of improvement. So, in fact, construction of codes is different, but vaguely in the spirit of this construction of codes, does go back to Zipser and Spearman, their failed approach to prove the PCP theorem this way.
So there is another component to it, is that Omer-Reingold's proof for the undirected graph connectivity being in logarithmic space. So that proof has much like the structure of Dinour's proof, and it was like a year earlier than Dinour's proof, and I think it was a very inspiring result. I mean, for many reasons, it's just for that, but that had this kind of structure, and it's just coincidental. It's an open, or I think it's a very interesting question, like to actually to connect Omer's theorem, which is a completely different theorem, to like Dinour's proof somehow. I also want to maybe mention another thing about these two different proofs, is that so they are very different actually in the following sense, that like in the original proof, like first there is a huge gap created. A huge gap meaning that we create some kind of constraint I mean, it's not a constraint satisfaction problem, but some kind of satisfaction problem with a huge gap. And then, but then that's not a constraint satisfaction problem because it does not read constant bits and so forth. So then, by various structural changes, like we make it what it's needed, but then we lose the gap, but then the gap still becomes like a constant gap. So originally the gap that blows up to, I don't know, 1 versus 1 over n or something like that. And then during the transformations, the gap decreases. So in Dinour's proof, actually the gap at every step, well, as Luca said, gradually increases, right? Because she has this gap increasing transformation with the expanders. And that was a new gap increasing transformation, which actually kept the structure better than other gap increasing transformations. So the original gap increasing transformation, well, that did terrible to the structure, but it increased the gap hugely. And then there was another gap increasing transformation, which was the parallel repetition, which did actually quite well with the structure, but then it increased the instance size hugely. So Dinour's gap increasing transformation is so modest with changing the structure so that's why we can just do log n iterations of it. Like with the other transformations, like doing more than constant number of iterations would be a complete killer. So these are very different proofs in structure. And I'm just saying that because if you want to duplicate like it in the quantum, then we might have to choose like which structure we like at all. It's not clear.
So one could see, sorry, before that to follow up, that you could see what's happening in the prior repetition theorem as being the non-de-randomized error-correcting code construction where you simply kind of start from a code and then for every k-tuple of coordinates you write it down. So then you need to de-randomize this with expanders if you want the new encoding to still be linear in size compared to the other. And as Mario said, for sort of approaches that keep the number of queries constant and make the gap better, the parallel repetition theorem was the only result of this kind. But there was a result of Fag and Killian that showed that the parallel repetition theorem cannot be de-randomized. So that if you, in the setting of the parallel repetition theorem, you construct k queries for the two provers, but not independently with some pseudo-random distribution. No matter what this pseudo-random distribution is, there will be some case where the provers do better than you would expect. So what goes on in its proof is not a de-randomized parallel repetition because that cannot work, but it's something that is so similar that, so there's one more reason that it was so unexpected that it would work. So I guess again the conventional wisdom was that the true meaning of the Fag and Killian impossibility result is that there is nothing that can be done to kind of improve the gap without blowing up the instance size. Yeah.
So this is a question from Patrick Hayden. He's watching this live and he thinks it.
Okay.
So he's
Where's the
asking,
camera?
can you say a bit more about how the toy error correction questions relate to proof systems?
So there isn't any kind of generic transformation that if you have an error correcting code, it can become a proof system. But so if you have error correcting codes with certain additional properties, then they can yield proof systems. And those codes, they do have those additional properties. And so when you're able to get all the coding theoretic parameters nicely, it also implies that one gets good proof systems. But what those additional properties are, it's a very long story, so it's hard to summarize. Oh, if you want to try.
Well, I just wanted to say that so when we teach the PCP theorem, we always try to teach, or not always actually, I think I learned a lot of new things, especially how to teach the Nurse proof. So we always try to teach it through the error correction code analogy, because that's the baby version of the PCP theorem, because PCP theorem isn't, because it is a sophisticated error correcting code, and as Luca says, with extra properties. And when last time I taught it, I was actually trying to develop a framework in which is a sort of a generalized framework which generalizes error correcting codes and PCPs, which I call knowledge verification systems. So the essence of that was, although I've never written it down, but the essence was that in the case of codes, we verify simple knowledge, just simply that like this string is the same as that string. And in the PCP theorem, we verify like a more complex knowledge that like that this is a proof that this three-set formula is satisfiable. And so there is a system can be defined, which I call the knowledge verification system, that like does the simple thing with certain parameters or whatever, and does the more complicated thing. And but it would have been nice to have like a continuous kind of way of going from the simple to the complicated, and I don't think I achieved that. And so we still teach it like Luca, that so we just say the simple thing and then we say that the complicated thing is just the same, just more complicated. So I'm sorry, that's what I just wanted to say. So, are there questions? So if not, then thank you again.
Yeah.